Hi everyone, my name is Travis Collins. I'm with Analog Devices. So just a little background on myself. I've been a GNU Radio user for about, say, 10 years now. I remember the days of like using Bootstrap before this whole CMake overhaul back in my master's and PhD days. About 2 years ago, or 3 years ago now, I joined ADI and I took over the gr-iio, or the I/O interfaces from Paul. And I've kind of continued the great work that he's done. And in the presentation, I'm just going to give kind of an intro to I/O and how the kernel framework that we use to develop drivers works, the library that we use to talk to those drivers, and then how GNU Radio interfaces with that library. Then I'm going to talk a little bit about some of the libio isms that might exist that might be a little confusing or has been confusing traditionally for users. How you can use libio and gr-iio to access custom IP that might exist in your FPGA. We'll talk a little bit about I/O performance, some of the current state of libio, and some of the new things that we're working on. Then I want to talk about some new features in gr-iio that are kind of in progress and should be merged soon. So if you have a Pluto or an FM comms or an ADRV, these really apply to you. And then finally, I just want to talk about the gr-iio grep that we have, the enhancement proposal to merge gr-iio into mainline, just to make it easier for everyone to use, and just kind of the activity that's going on there. Okay, let's kind of get into the basics of I/O and libio. Now, if you're not familiar, I/O stands for the Industrial Input-Output Framework. This is a kernel framework that's designed for generic ADCs, DACs, sensors, kind of the things that don't fit into HWMON or the input framework, which is for like keyboard, mice, that kind of thing. So it's kind of perfect for the devices that ADI works on. But this is not a ADI-only thing. Our competitors, other vendors have tons of I/O drivers from temperature sensors, pressure sensors, all kinds of things. And the gr-iio blocks kind of allow you to access all kinds of different devices. So it's not just SDRs. It's like IMUs, it's temperature sensors. You can control amplifiers or generic IP using I/O drivers. And we'll pretty much focus on SDRs because that's kind of the most interest in this community here. And we have drivers for obviously like our products like Pluto and this radio on the right. The guy here in blue is part of a kit we call PackRF. As well as we support even third-party radios like the Sidekick here and even the Edis E310. We have actually a full SD card that works on that product, and you get I/O support. And it controls even the external filter banks. Now, the big question is, how do you go from that I/O driver into GNU Radio? And this is what I'm going to try to break down for you so you understand it a little bit. I'm just going to start at the driver level first, and then we'll kind of talk about how the I/O pieces come into play. There's a lot of complexity in chips. For example, this is kind of the simplified diagram of the 9361. The part has over 1,000 registers, a lot of state that you need to maintain, and we do this through an I/O driver. And you can't just connect a USB and magically it works. There's a lot of pieces that happen in the back end in the FPGA, in the ARM, where the driver lives to make the part work. Now, a more kind of appropriate perspective to have is more of like a system-level guide, where we have a physical piece of hardware on the right, so like a transceiver, 9361 in this case, Zinc, where we have the programmable logic, and then the PS here, the ARM, which is running Linux. And then the far right, we have a host machine that's running GNU Radio or some other application that we want to interface with the radio or some other device. But generally, this doesn't have to be a transceiver here on the left. It could be a sensor or a generic device that has an I/O driver. Now, I/O has this very hierarchical structure. So at the top, we have this concept called contexts. And contexts can be local, they can be remote. And a context will be, I would say the best way to think about it is like a board, or a laptop can actually be a context. And a context will have devices that are associated with it. So On Pluto, you'll see devices that are the transmitter, the receiver, the PHY, which is kind of like the overarching driver, as well as a power monitoring chip, the ADALM-1177 you'll see. Here we just have an example of what maybe like an IMU might show up as, where we have attributes that are associated with it. So the device itself will have attributes like sample rate or more kind of complicated attributes that you might not want to play with at all times, where they're called debug attributes. They're not really for runtime or common uses. And then when we want to deal with buffers or pulling data back from the device, from like a converter, then we have these buffers and these channels. And they have attributes associated with them, like the length of the data, the type of the data, the signedness of the data. And this is how we can describe a very different number of devices. So if you want to interface directly with the I/O driver, you can go through the sysfs API. You can log into, say, Pluto. You go to sysbus IO device 0, and you'll see a number of file descriptors there. So there'll be like name, which will be a device attribute, and you'll see some that are like hardware gain, which will be channel attributes. And these allow you to directly interface or control different parts of the hardware. So here at the bottom, we're simply using cat to pull out the name, and then we're echoing a value into hardware gain, and we're pulling that out and getting the actual hardware gain that's written to the device. And I/O is designed to be friendly to the user, so it provides data in scientific units or relative units. So you'll get data back in like volts, amps, dB, things like that. So going back to that system level framework, here we have that driver, that I/O driver that's specific to a device that lives in the kernel that's running in the ARM on the board. And you can interact with it directly through the sysfs API. Now, using sysfs is great for kernel driver developers, but when I want to change the gain of my radio and I have to SSH into the board and cat and echo something in and out, that's not really great. And when you're using a device as complicated as the 9361, you have to set tons and tons of attributes, and that's really no fun. As a result, this library that was designed for interfacing with these attributes was developed. This is called lib-io or the lib-io. And it's a C API where we have a number of bindings for C++, C#, Python, MATLAB, and you can interface a lot more easily with these attributes. And it handles things like buffer maintenance and things like that, and error handling. And it makes it a lot simpler to interact with the devices. Now, if we kind of go back to that picture, now we have this lib-io library that's living on the board. And this is calling into the I/O driver that's in the kernel, and then that is talking to the physical chip itself. Technically, you can run GNU Radio on the board, and we do this in our standard SD cards for our FM comms boards that come with like a ZC706 or a ZC102. Some people have got it to work on Pluto, but the conclusion that they came to was like, this was interesting, but don't do it. It's not a great experience when you have a single core ARM at 666 megahertz. Now, the question is, this is great for an embedded platform, but how can I interact with Pluto from my host machine? And to do that, lib-io has this concept of backends. And backends allow you to directly remote into a board or use the same lib-io API on your host machine and talk to the device. This is kind of like an RPC, if you're familiar with that concept. If you look on Pluto or any of our standard eval boards, and you just look at the processes, you'll see this little process called IOD that's running, and that's responsible for doing this translation for you. So if we look physically at how this is kind of laid out, where we have a machine on the right here, the development board on the left, we have lib-io on the right, and it's calling over the network to that little IOD daemon, and that's doing the writes to the part through lib-io. Okay. We do support a number of different backends, from Ethernet, serial, like USB, PCIe, a number of different options that you have depending on the bandwidth that you need or the simplicity that you need or the board that you have. And this is what applications like gr-iio are using. This is what MATLAB uses to talk to the device. This is what grqx is using, SDR Angel. All these open source projects, if they want to talk to Pluto, they're using lib-io under the hood. Now that kind of completes the picture for us. Just to quickly go over that again, from the chip, that's interfaced through the FPGA, which has the I/O driver, which will be talked to through lib-io, which is then interfaced with IOD, that little daemon, and then that will do the translation from the network or USB from lib-io that's on your host. And this is how we're moving data back and forth and controlling the device. Okay. But the great thing about this is it's very transparent to the host machine. So this could be a Pluto, it could be one of our SOM boards, it could be a more traditional FMC card that's connected to an eval board like a 706 Z board, that kind of thing. And you don't have to have a transceiver on the left. It could be a standard sensor or some other device that has an I/O driver. Okay. But like any good library, it has standard command line tools. So if you want to change, say, the sample rate or the LO frequency or some device attribute, you can directly do that. You can directly access registers if you want to do that. So you have a number of command line tools from directly accessing attributes, finding devices on the network, reading and writing from buffers. If you want to get really low level on the device, you can do that with these tools. But if you want to crank it up a little bit and pull some data and visualize that, we do have a completely open source application called IOscope. It has this plugin concept, so you can add other devices. If you have a custom board, if you have your own I/O drivers, they'll find them in IOscope, and you can add your own plugins for those boards. Okay, now let's talk a little bit about the GNU Radio interface. When you install gr-iio, it will come with a number of blocks. These are SDR-specific blocks, device generic blocks. So if you have your own I/O device, you can use our generic blocks for that. We have attribute blocks, which are used for accessing device debug registers if you want to do that directly from GNU Radio. And then we have these kind of extra ones, these math blocks. And these are actually part of Scopy that are run under the hood. So Adrian talked about Scopy yesterday, about how we use GNU Radio, how we use flow graphs under the hood, and that's why those blocks exist inside gr-iio. But they're actually super useful for other things besides kind of instrumentation. You can do generic kind of functional math inside those blocks. Now, the blocks themselves have this inheritance structure. At the base, we always have a very basic block. So we have our I/O device source block for source devices, and then our FMCOMS2 simply inherits from that device. And then Pluto is really just a subset of our original FMCOMS ports. And if you look at the code, you'll see that it's just simply inheriting, and there's not a lot of duplication all over the place. And since these I/O device sources are so generic, you can actually create your own versions of these blocks. I kind of do that all the time for debug and test. People have created them for other third-party radios. I know a number of users that have done that for the Sidekick radios that are using our Pluto images on those devices. Now, kind of a confusing topic that comes up all the time is how do I set contexts within the I/O blocks? So again, contexts are how we address a device, and they can be local, they can be remote, but setting it can be kind of a mystery to some people. Now, the context or the context is addressed through what we call a URI, which is simply an address that you use to talk to the device. And it's structured by the protocol and then the address. So for IP, it would be IP and then the address. USB would be USB and then the address given out by libUSB. And if you're physically on a board or you have local I/O devices, you can simply use local. On my Linux laptop, the gyroscope inside it actually shows up as an I/O device, and I can pull that right into IOscope. I can pull that device into GNU Radio, and I can look at the gyroscope data as I rotate my keyboard, which is pretty interesting. Now, there are some kind of special things that you can use inside the GNU Radio blocks for URI. If you leave it blank, it will do auto discovery. For Pluto, if you leave it blank, it will just pick up the device automatically. So this doesn't work if you don't set a specific global attribute or a global variable for network devices. However, you can simply put IP and the host name of your board. So for us, our standard boards are analog, that's the host name. Pluto is pluto.local. And when you fill that in, it will use Avahi under the hood, if you have that installed, or Bonjour if you have like a Mac, and auto-find the device automatically. Which is, this is kind of like a little-known feature that you can do. Okay. Now, when you add multiple blocks into a flow graph, they'll actually share contexts if you use the same URI. So if you use here IP pluto.local for both blocks, they'll share the same URI when they're talking to the device. And this is great. This even works if you're talking to physically different components on the board. So here, I just printed out the different devices that are available on this, this reference radio that we have. That's part of our PAC-RF kit. And here I have an individual block for the IMU sensor that's pulling out acceleration data, as well as for the transceiver itself. And both are using the same URI, and they'll use the same context to talk to the board. And this is automatically handled in the flow graph. Now, if you have separate context names, say, for example, if you have 2 Pluto blocks, Pluto.local, and you're using the URIs Pluto.local and the standard IP address that we give to Pluto, this will actually work. Now, they actually do not share a context. They have separate contexts when you're talking to boards. And what will happen is that IOD will send interleaved data to each board, or to each source. So the first buffer will go to the first device. The next buffer in the queue will actually go to the second device. And it kind of goes like that back and forth. So just be careful if you set up a system like this. It will work, but kind of the outcome might be something unexpected that you have. But this is really useful. For example, if you want to run a flow graph and you want to use some external tool to modify some attribute in the part, this is a special feature of the IP contexts. With USB contexts, it actually pulls the context away so that no other application on your machine can actually talk to the device. So if you need to, say, use I/O scope and GNU Radio together, use the IP context, and it will allow you to address the device. OK. Now let's move over to talk a little bit about custom IP and how we can talk to that on our remote systems. Now, why should you care about this? So it's not just offloading heavy processing to the FPGA. Doing things in the FPGA is really useful for tight timing applications, where, say, you're doing radar and you need tight coupling between transmit and receive, or you're doing frequency hopping and you need very tight control over what frequency you're on. And you doing things over the network or over USB really is not the best way to do that, because there's inherent latency in those designs. Or, for example, if you're using a like a slotted Mac, like a time division multiplexing Mac system, doing things in software is not always the best option. And this is why it's really useful to do things on the FPGA. However, I would say that the standard tools that are provided by a lot of vendors don't make it easy to talk to IP that you generate. Vivado HLS is a great tool. DSP Builder are great tools. They get your IP on the board. They make it simple. But actually talking to that IP can be challenging. And talking to that IP remotely can be even a bigger challenge, because there's really no standard tools to do that. And that's why things like RF-NOC are really great, because they allow you to kind of bridge that gap. They allow you a lot of software control over IP that you might deploy. And we can do something similar with lib-io and IO. Now, let's kind of look at an example of where this really might be useful. There was a paper done in 2016 about the frequency hopping capability of different SDRs. And on the right, I just have a table of some of the results. And they say that the B200 and the E310, all which have a 9361 inside them, or a 64, I believe, for the B200, all have a super long frequency hopping capability. And this was all done through software, so there would be a simple start hop, finish hop, kind of check if the LO was locked, and then that time was measured. And this was on the order of milliseconds. Now, in reality, the part is actually capable of hopping at 25 microseconds, so much, much, much faster. But to do this, you have to be able to keep up with the part at that speed. So if you want to hop very quickly at this rate, you have to use this concept called fast lock profiles in the transceiver. Now, if you don't use these in a traditional manner, you have to, so you kind of have this logic on the left here in the default LO mode where if you change the LO beyond 100 megahertz, you have to retune or recalibrate the VCO. And this can take a lot longer than that, hundreds of microseconds in some cases. Now, in the case of fast lock profiles, what you can do is simply save a number of these calibrations in what we call these profile registers. And then when you want to move to the next one, you simply tell the part, hey, load this profile, and it will simply change, and the LO will shift and lock in 25 microseconds. Now, this can be done, or this can be controlled in two ways. Here we just have a little diagram of the chip itself and a baseband processor. So this would be your zinc that's actually physically connected to the part. And you can talk to the part over SPI, or you can talk to it through these control pins. And SPI will actually keep up with the part if you want to hop at that rate. However, it's not as deterministic. So if you need like sample level control, you really need to use the control pins to be able to control that hop. And a kind of a way that you could set this up would be that you have this hop controller. So this diagram is so we have the PL in the middle, so our fabric, the PS on the left with our kernel in it, and then the chip on the right. And we're talking to the chip through those control pins and then reading them out so we can make sure that the baseband PLL is always locked. And then we could use this hop controller to basically control these pins, tell the part when to hop, and then control the DMA data so that during those transitions, we don't allow any data into the DMA or out of the DMA back into the part. And if you're curious about this design, it's actually documented on our wiki, so you can understand how it's structured. And this was implemented in the FPGA. And then we actually wrote a little driver for it in I/O. So there are kind of two ways you can go about, so traditionally, there are a lot of ways you can develop drivers, but this is a common flow I use. I usually start with this kind of stump driver that we have, a really basic driver. This was actually developed by the MathWorks to talk to I/O devices, and it exposes just registers of the device. So if you want to get at the registers of a specific IP, this is a really simple way to do that. We have a patch available that will add the driver to your kernel, or you can use the standard kernels from MathWorks. And so it's in the support packages for E310, FM-Comms, ADRV, the standard boards. This is great for debugging, but all the logic or the control of the driver is on the user, and they have to kind of manage it. And it's not, I wouldn't say, it's not a great portable solution. And when you want to kind of do something that's more portable, you develop your custom driver. And this is what we did for this application. So let's actually see this working. This demo actually runs on this board I'm showing here, which is our ADRV 9361 SOM. And the test, I'm just using the SOM that's, so transmit is connected to receive, so we can just see what we're transmitting. And I'm going to be hopping or moving the LO using this fast lock controller that we built. And it will just continuously hop the transmitter, and we're just going to be observing that on the receive side. So in this flow graph, I have a FM-Comms source in the middle here that's just being sent out to some frequency plots. And then on the left, we have some attribute blocks that are actually controlling that I/O driver and setting different attributes. At the bottom, I'm simply pulling out the different, listing of different drivers. We can see that the Hopper driver is there, and we can see that the 9361 PHY driver is there. And now I'm just going to start the flow graph. And we can see the tone that's being transmitted by the DDS that's in our standard reference designs. Now next, what I do is I load up the fast lock profiles individually. So I move to each LO, and I save the calibration data off into the part. And you can see that the tone is just moving across the different frequencies that I'm using. Okay, now I have all the profiles loaded, and what I'll do is I'll turn on fast hopping. And you can see it just hopping all over those frequencies. Now, it is smearing just because we're not keeping up with the device, so it's not a real-time spectrum analyzer. And what we can do is actually change how long it spends on each frequency, and that's what I'm doing by changing that slider. And you can see that the lines are not smearing anymore, just because we're spending more time on those frequencies. So that's just an example of kind of the control and the way you can use I/O to control external IP. And this is a really easy way to get at really time-sensitive things in the chip, to get at IP from GNU Radio, or since it's an I/O driver, you can get at the command line if you want to, and it's really, really portable. Okay. Next, I'm just going to talk a little bit about libIO performance. So we had a really interesting talk the other day about E310 and pulling data off of it at speed. How we do this is with a kernel driver, and inside the kernel driver is a ring buffer that we use. So when you pull data from the chip, the DMA puts it into this ring buffer, and then you pull from that ring buffer, and that's what you're seeing in GNU Radio on board. So this is an MMAP device. It's super fast. It's really limited from our experience by the memory controllers in the FPGA. So we use it for gigasample devices, and it keeps up pretty well. However, when you're using remote contexts, this is a little bit different, how you interact with the device. So it has this synchronous transfer mechanism, where for every transfer, you have to do a buffer pull request. So you request a buffer, it gives you one. You request a buffer, it gives you one. So you have to deal with this latency of doing a request every time. So this will actually cause a roughly 30% overhead from the ceiling of your platform. So in libIO 2.0, we're actually looking at modifying this to do a more asynchronous transfer. So you do a single request, and then you just keep pulling buffers back, and this will give you a lot more speed. Okay. And just for reference, if you can use local context, please do. This is kind of just an example of the overflow occurrence probability. With local contexts, you can pretty much max out the device, but with IP, increase your buffer size, and you'll do much better. Okay, so I'm just going to quickly go over some new features that are in gr-iio that are coming out soon. So we're adding a lot more filtering control, or filter configuration control in the blocks. We're doing this by adding a filter tab to the FMCOMs and the Pluto blocks. So you'll have options to either turn off filters, provide some auto preset filters. You can load a filter file from our filter generation tool, or you can use this new feature where you can design a filter on the fly using just some simple parameters like f-stop, transition band, the analog bandwidth, and we take all those into consideration and design a filter on the fly for you. We're adding underflow and overflow indicators, so the standard like O's and U's that you're probably used to from UHD, they'll be provided now across all our blocks. We're enabling the FPGA filters that are inside Pluto. If you didn't know, there are additional decimation and interpolation filters inside Pluto. And this will allow you to get down to 65 kilohertz sample rate. You don't have to do anything. You simply install the new blocks, and you can set the sample rate lower, and it will turn on those decimations for you. The last feature is we're adding a DDS controller block. If you didn't know, there are DDSs inside Pluto and inside all, or pretty much all of our reference designs. And we have a block that you can independently control that through GNU Radio now. Do I have time for another video? Or nope? OK. Come to the workshop later if you're curious about this. Just an example of how the DDSs work. And just a final note. So we do have a grep open to mainline gr-iio. And we're doing this because we want to make it easier for everyone. So you don't have to go to our out-of-tree module. And we're always being pushed to maintain all of our blocks to keep up with GNU Radio development. And we're doing this by the grep actually proposes to remove just the scopy blocks that are in, and you can conditionally install the device-specific blocks, or just pull in the standard streaming ones. Okay. Just a final note, we are adding Python bindings. So if you want to use Python for talking to our transceivers or different devices, we have a new simplified API that you can install from pip today. So if you don't want to write a bunch of lib-io code, this is just setting up the transceiver and setting 2 parameters. And this is setting, let's see, like 8 here, 7. And it's a lot simpler to interface with the transceivers. OK. Thank you, everyone. If you have any